Okay, so welcome to the session for today. So let us have problems on a simple strain. So as we can see here, we have here problem number 1. So it refers to a tension steel test wherein both ends of the specimen is grip, where the steel test is limited to a 600 millimeter length and a 20 millimeter diameter rod. So basically, the load were recorded as follows. So on 57.2 kilonewton, it incurred a deformation of 0.45 millimeters, and then 171.6 loading, we have a deformation of 0.4895 millimeters. So it is required that we compute for the strain due to the 57.2 and 171.6 kilonewton load. At the same time, we will get the Young's modulus of elasticity. Okay. So here, of course, yung formula na alam natin is we have sigma is equal to P over A. And then from this, we will first determine the stresses that corresponds to these recordings. Okay, so for 57.2 and 171.6, we need to determine the area of that bar. Okay, so the area of the bar is computed as a circular one. We have pi over 4 times 20 squared, that is equal to 314.16 millimeters squared. So here, we can now compute for the stress due to 57.2 kilonewton first. So we simply divide that by the area, that is 314.16. So by this, we will yield at a stress of 182.07. So for letter A, the corresponding strain due to this loading is equivalent to, of course, we know that the formula for strain is deformation all over the length. And the recorded deformation is 0.2145. We'll just simply divide that by the length, 600, and we come up with this, 3.575 times 10 raised to negative 4. So this is actually unitless, or millimeter per millimeter. So here, we have already obtained the stress and the strain, the corresponding strain for that. Okay, so similarly, we're going to do that for the force equivalent to 171.6. So if the force is 171.6, okay, divide lang natin yan sa area. Again, we have 546.22 for that. So for each corresponding strain, we again apply this one. The recorded deformation at that force is 0.4895 divided by 600. We'll come up with 8.158 times 10 raised to negative 4 millimeter per millimeter. Now, for the Young's modulus of elasticity, we will utilize the slope because out of this 2 points, there will be a slope in it. There will be a vertical difference, that is delta sigma or delta stress, and a horizontal difference between these 2 points. We have delta strain or delta epsilon. So in short, we have a vertical and horizontal slope, and actually we have a right triangle here, okay, obviously forming a right triangle. So by this, of course, we'll just subtract what we have obtained a while ago, 546.22 minus 182.07. To. We have this 546.22 minus 182.07. We have the change in stress of 364.15. And then the change in strain, we will also deduct the second value to the first value and come up with 4.58 times 10 raised to negative 4 millimeter per millimeter. So we should note that these values are within the proportional limit. When we say proportional limit, we have a straight line or a linear relationship on those points, okay? So by that, we simply apply the formula. Of course, the Young's modulus of elasticity is just simply equal to stress all over strain. But we are now referring to the slope. Just place there the change in stress all over the change in strain, because we have actually referred to a 2-point here. Okay, so by dividing that one, we will now have the Young's modulus of elasticity to be equal to 794,566.88 megapascal for that. Okay, so this is the answer for letter C. Okay, moving on to the second problem, we have stress and strain given. So as we can see here, we have for a stress of 41.33 megapascals, there will be an elongation of 106.67 times 10 raised to negative 6 millimeter per millimeter. And then increasing the stress to 100 megapascal, the strain, the deformation also increases to 258.09 times 10 raised to negative 6. So we are tasked to compute for modulus of elasticity, the strain for stress of 60 megapascals, the original member length for an elongation of 0.4 millimeter, and a stress of 60 megapascal. So in here, stress is already given. Okay, so strain is computed out of the deformation. Of course, strain is just equal to the deformation all over length. So all you have to remember that the deformation just distributed to the whole length, and then this is sigma is equal to P over A, or the loading is equally distributed all over the cross-sectional area of the material. Okay, kaya nga tinawag itong sigma is unit load at ito unit deformation. So take note of that. So next, as I have been saying, modulus of elasticity is derived by the slope again. So similar to problem number 1, we'll just have to get the change in stress, okay, and then of course the change in strain. So just simply subtract those values. So itong 258.09 millimeter per millimeter yan. Millimeter per millimeter. So kapag millimeter per millimeter, it is understood that this is strain. Okay, so diretso na tayo, no? So we'll just subtract those one and come up with these values, and then out of that, stress is equal to modulus of elasticity E is equal to stress all over strain. So here we're going to have this one 58.67 all over the strain 151.42. Then we will come up with this value 387,465.33 megapascal. So what is the corresponding strain at 50? So I think clerical error to, no? Dapat ito is 60. So this should be 60. So again, what is our basis? Remember that the slope already is defined by E. Yan yung slope kasi ano yan eh. Change in sigma all over change in epsilon, or ito delta y or all over delta x on the x and y plane. So therefore, we'll just be utilizing now similar triangles. So what is the corresponding strain on 60? Looking at the ordinate or the y axis, we project that one. Here it is. So ano yung katapat nito? So that is the question. What is the strain on this portion? Okay, so as we can see here, we have actually two right triangles, the bigger one, the smaller one. Whatever the slope of this bigger one is also the slope of the smaller one. So therefore, we will now be working with these 2 points. So this is 40 and the 60 point. So we have already derived E here. Just simply substitute that one. What is delta strain? So actually ito ang ginamit pala dito is 100 or the higher value. But also you can also use any of this. Basta adjacent siya sa point na yan. So dito tayo sa 60, ito yung 40 at ito yung 100. So in this solution, ginamit niya po yung 100. So the higher point, so the higher point here, and utilizes this triangle. So ayun, ano yung delta sigma niya? Delta sigma is just simply the y here, 100 minus 60. So this is it, 100 by 60. And of course to delta E on that delta sigma or delta epsilon at this triangle. Okay, yun muna. So out of that, delta epsilon or the change in the strain is equal to 1.03 times 10 raised to negative 4. And then we already know the sigma at 0.2. Ito nga, ito yung 0.2 at ito yung 0.1. Kaya nga alam na natin yung 0.2, ang 0.1 ang kinukuha. We can get that by this delta strain or the change in strain. So 1.03 is substituted here. Ito given na yan, 258.09 times 10 raised to negative 6 minus the strain at the 40 point or the 40 megapascal stress. Okay, so by this we can now get the corresponding value for that is equivalent to 1.549 times 10 raised to negative 4 millimeter per millimeter. Okay, so what would be its member length at this instance? So perhaps we can go back to the unknown, the original member length. Ano daw yung original member length for a stress of 60 megapascal and a deformation of 0.4? So that is the question. So we simply use the formula of strain that is equal to the deformation is distributed all over the length. Of course, ito na yon yung strain natin, 1.549 times 10 raised to negative 4. At yun na yung deformation, 0.4. And then we can now compute for the length. Okay, so again, this is a length. It's not an E. Okay. So L now would be equal to 2,582.31 millimeters. So in short, this is 2.558 meters. If we wanted to have a deformation of 0.4 with a corresponding stress of 60 megapascal. So let us note here that at this point, all of the values will return, or all of the deformation will just return to its original setup, or meaning wala pa tayong yielding. Kahit na na-release yung loading, ibig sabihin walang permanent set. So it will go back to its original length. So there is no permanent stretch, okay, or permanent elongation for those values of stresses. Okay, so moving on to the third problem, we have here a recorded stress and strain. Okay, so stress and strain na kagad. We are going to compute for the modulus of elasticity, modulus of resilience, and modulus of toughness. Now, if we are going to graph this given data here, the stress versus the strain on the x-axis, so we can come up with this type of curve, and then we can get here an obvious fracture point. Okay, obvious fracture point, because dito nagkurba na yan, and then we will have a point beyond the elastic limit, or sorry, a point beyond the proportional limit, di ba? Ito yung proportional limit. So right after this, we have yield point, and then elastic limit, and then we have ultimate strength, and then the fracture, or the failure, or modulus of failure. Okay, so as a solution, so the fracture point, or the end of the proportional limit, is at the first point where the stress is 152.67 megapascal with a corresponding strain of 0.000533. So yun pala, sa umpisa pa lang, ito na yung fracture point that is measured from 0, straight line siya hanggang dito, straight line siya hanggang doon. Okay, okay. So kapag straight line yan hanggang dito, then we will simply divide this one, 152.67 all over strain 286,435.27, because ayun, we are just working with the 2 point. Yung isang point kasi nasa 0. That is why we do not need to have any pair of the change in sigma or the change in epsilon. So by this, we can derive the modulus of elasticity equivalent to 286,435.27. Okay, so as for letter B, what is the modulus of resilience? It is obvious in the figure na yung modulus of resilience is just simply the area bounded by the straight line or within the proportional limit. Yung nasa ilalim ng proportional limit, that is our modulus of resilience. So madali lang yan, we'll just have to get the area, 1/2 base times height. The base here is of course, that is strain, with the corresponding height of the stress, 152.67. We have an answer of 0.0407 megajoule per cubic meter. So how is that how was that derived? Ito, alam naman natin na yung ating base is unitless, pwedeng meter per meter. So ibig sabihin, megapascal is being multiplied by meter or millimeter per millimeter, or pwede rin na imbis na millimeter per millimeter, pares mo sa meter per meter. So in short, megapascal is meganewton per square meter, di ba? So papares natin sa meter per meter, meganewton meter per cubic meter. So ano yung meganewton meter? Actually, newton meter is a unit equivalent to joule. That is why ang prefix niya dito is mega newton meter. So that is joule or megajoule per cubic meter. Okay. So that's it for letter B, modulus of resilience. Pag sinabi nating resilience, it is adaptable to any loading. So there will be no permanent set yet. The material will tend to go back to its original length whenever the loading is released. Okay, letter C, the modulus of toughness. Ito, yung modulus of toughness, lahat ng area bounded by the curve. Okay, we will be having this. So we will be having how many area? 5 areas for that. Anyway, lahat naman ng points niyan ay given. Okay? So all we have to do is to compute for that one. Ito, area 1 yan. Ito yung area 1, yung triangle. At ito yung area 2. It is assumed na ito, trapezoidal, and area 3, of course, trapezoidal din yan. Area 4, halos rectangle, pero trapezoid pa rin yan. And trapezoidal area for area 5. So anyway, recalling the area for a trapezoid, just have to get the average of the two bases, okay, and then multiply it by the height. So this is what is done here. Okay, so the modulus of toughness came up to be 0.273 meganewton per cubic meter or megajoule, meganewton meter per cubic meter or megajoule per cubic meter. Okay, so that's it for the problem, for the third problem. So we proceed now to the fourth one. So in here, yielding was observed in a stress strain test when the load 20 kilonewton was applied to 1.2 meter long structural member. Calculate the allowed axial force to the structural member to satisfy a factor of safety of 2 with a corresponding elongation of 0.6 millimeters. Assume working stress equivalent to 400 megapascal and Young's modulus of elasticity to be equal to 200,000 megapascals. So for that problem, yielding was observed in a stress strain test when the load is 20 kilonewton. So ito, the principle here is the relationship between the yield stress as well as the allowable. So it is expressed in terms of factor of safety. So let me just write that one. So Fs is equal to, this is the sigma along the yield point all over sigma allowable. So sigma y is actually the working stress at a certain loading. Kapag may loading, certain loading and an area, you can determine the unit load for that. So the stress is determined by this. However, in proportional limit, within the proportional limit, it is very difficult to determine the yield point of the material unless you're gonna test it to tension steel test. That is why ginagawa na yung working stress, instead of working stress, it is also equated to a yield stress or the stress wherein the yielding of course. Now, if you're going to have a certain stress before this yielding, because we do not want that the material will be stressed until the yield point, we will be having a certain allowance before the value of the stress at the yield point. Parang if you are going to buy a cooking oil, halimbawa, you are from Bulanao and you were instructed by your mother to buy a cooking oil on a store that is located somewhere in San Juan or Dagupan. Kung 20 pesos yung oil, plus yung pamasahe mo, 15 pesos, plus another 15 pesos. So, ilan na yon? 30 plus 15 plus 15, that is 50 pesos. So, yun lang bang hihingin mo? Of course not. So, hihingi ka probably 100 pesos for your money to buy the said cooking oil. Same true if you're going to have a credit or loan. Kapag nag-loan ka, syempre, halimbawa, you have a hospital bill of 30,000. So, I think, baka yung 35,000, kulangin mo pang utangin in order to secure your hospital bill. Of course, you do not want to have an exact amount. Kaya nga sinasabi natin, mas mabuti pa na sobra kaysa sa kulang. Ganon din dito, in engineering, of course, you wanted to have a design value that is conservative. When we say conservative, meron pa siyang allowance before na ma-reach niya yung sigma. That is what we call the factor of safety. It depends on the designer actually, Kaya nga yung halimbawa, pag nag-design ka later on, if you are a beginner, so you do not want na na eksakto yung design mo, wherein you will have a factor of safety for everything you design. Okay? So yun. Ito, working stress is also the stress at yield point. Kaya nga sigma y, the stress at the yield point. And this is the stress incorporation of the factor of safety. So the stress you wanted to have before the sigma on the yielding. Again, this is much lower. Dapat mas mababa yung allowable stress comparing to the yield stress. Okay? So in this problem, yung factor of safety is set to be 2. So yung factor of safety is 2. Then the yield or the working stress is 400. Okay? So we can now get the sigma allowable. Okay? So getting that one by cross multiplication, that is 400 all over 2. The allowable stress is equal to 200 megapascal. So ito lang yung dapat na kapag nag-fail man yung material sa 200, malayo pa siya. Malayo pa siya sa 400 megapascal na yield point or the yield stress. When we say yield stress, kapag 401 na yan, it will have a permanent set of deformation. So kapag ni-release yung loading, hindi na siya babalik sa original shape. Okay? Kung magkakaroon siya ng necking, so it will have a necking, di ba? Or what we call the tapering of the cross section. Unlike within 400 and below, gaganyan man siya at a certain loading. Pag release ng loading, babalik pa rin siya sa original shape niya. Okay? So that's the principle here. So yung mga stresses dito like 400, yun yung ito yung working stress. na tinatawag, kukunin lang natin yung area out of those allowables or the stresses coming from this formula, no? Yung mga stresses coming from this formula, our main objective is to get the cross-sectional area requirement ng allowable, no? Ano ba yung area required dito? Kasi kapag kinompute natin yung cross-sectional area at a certain yield point, masyadong mababa, okay? Masyadong mababa. Kapag ito yung kinonsider natin, maaaring manipis yung ating cross-section. But if we consider a factor of safety, considering the allowable stress, considering the area from this, or calculating the area from this allowable stress, then conservative yung ating design, no? So, again, factor of safety, dapat mas mababa yung stress before the yield strength. Okay? So from here, yun nga, sabi ko nga, kukunin lang natin yung area out of that. The formula is sigma is equal to P over A. So, anong gagamitin natin dito? Allowable stress. So, huwag mong gagamitin yung sigma y kasi yung sigma y, walang factor of safety doon. Okay? So, ano yung magiging area requirement at a certain loading? So, ngayon, sa substitute natin, we substitute the values here. 20,000 divided by 200, we have a requirement of 100 millimeter squared. Ito, na-consider na po yung factor of safety na 2, getting the 100 millimeter squared. So, ngayon, there will be a prevailing stress depending on the elongation as well as the length. Okay, kasi nga, we can derive the strain out of the deformation and the length. Okay, so in here, it was already given. All we need is to just substitute and then obtain the strain. So, ang tanong, kung may deformation na ba ganyan at length na ganyan, ano yung in-apply na load? Yun yung tanong. So, what was the loading applied? So, ngayon, we would like to note na hindi yung 400 at hindi rin yung 200 yun, ano? There will be a certain stress for this strain. Kasi nga, sabi ko nga, itong 400 tsaka 200, just to get the area or the cross-sectional area from that stresses. Okay? So, applying Hooke's law, we have a given here, 200,000. Okay, 200,000 is equal to the sigma or the prevailing stress when the elongation is 0.6 millimeters, and then divide that by the epsilon, 5 times 10 raised to negative 4. Then we will come up with a stress of 100 megapascal. Ito yung stress na yung applied load is 20 kilonewton. Sorry. So we are now not about 20 kilonewton, but it's all about this one. So it's not about 20 kilonewton, ano? It is all about the strain. Okay? It's all about the strain. Kaya nga hinahanap, ano ba yung loading para yung stress niya is 100 megapascal at the same time 0.6 yung kanyang deformation. Okay? So finally, we just substitute to this formula, sigma is equal to P over A. Okay? 100 yung nakuha natin, and then what is the loading, and then 100 din yung nakuha nating cross-sectional area out of the factor of safety as well as the loading. Okay? So, we will be having now a force of 10,000 Newton or 10 kilonewton from this equation. So, I would like to summarize the problem. So, sa problem, it was mentioned that yielding was observed during a stress and strain where the load is 20 kilonewton. Kaya nga, kukunin natin yung cross-sectional area out of the 20 kilonewton, considering also as a factor of safety of 2. Okay? Ito, hindi po ito yung actual na, hindi po ito yung actual na stress. Okay? Yung actual na stress is based from yun, yung kung ilan yung hinaba niya na 0.6 mm. So, kapag may deformation na kasi or an elongation, makukuha mo na yung strain, di ba? At kung meron kang modulus of elasticity, makukuha mo na rin yung stress. Again, 20 kilonewton here is just used to determine the yielding effect. Kaya nga, ayun, kinuha niya yung 20 kilonewton in solving for the area out of the working stress and that one, the allowable stress. Okay, so that's it for this problem. Okay, so moving on to the fifth problem, we have determined the required diameter and its elongation of the diameter of bar CD to satisfy a factor of safety of 3 when its stress at yield point is 276 megapascal. So, ang clue natin dito, stress at yield point, sigma y na yon. Okay? That is already sigma y. So, a factor of safety is applied, then the allowable stress would be equal to, ayan, simply just apply this formula. Okay? Gusto niya na factor of safety na 3, and the yield stress is 276. Dapat mas mababa dito yung ating allowable so that meron pa siyang allowance before failure will occur. So there will be a room for safety before failure. Yun lang ibig sabihin niya. So sigma allowable is equal to 276 all over 3 by cross multiplication. We're gonna limit our allowable stress to 92 megapascal. Okay, so ito na, solve for the minimum area out of this allowable. Okay, so we substitute 92 is equal to the force at CD or the cable CD all over the area. So we let this be equal to equation 1. Equation 1 muna yan because we still have to determine the force at CD. Okay, that could be obtained simply by mechanics principle. Ngayon, we'll just have to establish the free body diagram as we can see here. Ito, cable CD yan. Of course, when 1,500 kilogram will be applied there, it will be in tension, okay? Because itong pin connection dito, this will just side swing or it will have an up and down movement here at B, pero yan, it will stay or it will maintain the position at A, although ito pwedeng gumalaw yan ng paganyan. Okay, so by free body diagram, of course, kapag pin connection, we have two reactions for that, horizontal and vertical one, and then this one is tension or away from the joint. Let us just label that to be PCD or force at CD, and it is inclined at 52 degrees. So of course yung 1,500 dito class, ano pa lang yan, mass, so we have to multiply it by 9.81 to make it a force. So getting all the beam, we are now ready to take moments at A para naman ma-eliminate tong dalawang to because we do not need that one for a while. We take moments at this point. So meron tayong dalawang component dito. PCDY and PCDX. Yung PCDX have no effect when we take moments here because there will be no moment arm at that point. So, ang concern lang natin is ito. Ano bang force na yan? Kung titignan natin, that is, this component is opposite to the angle, 52 degrees. So, kapag opposite, we will use sine function. So, this is PCD sine of 52 degrees. So, that is why, counterclockwise yan, negative PCD sine of 52 degrees times the moment arm or the perpendicular distance from A that is equivalent to 2. Okay, so plus a clockwise moment from here, 14,715 times 4. Ito na, kukunin natin yung PCD equivalent to 37,347.2. So going back to equation 1, makukuha na natin yung area of the required area and then the diameter. Okay, because we wanted to determine the diameter of the bar. Okay. So, getting the square root or multiplication of the equation, we have 22.73 millimeter. Again, we apply the Hooke's law to solve for the strain. Ito yun. Strain is now equal to 4.6 times 10 raised to negative 4. Okay? Finally, in order to determine the length, ano ba yung equivalent length kapag ganito? Yun yung tanong. Of course, meron ka ng strain, meron ka na ring deformation. So, meron ka na ring LCD or the length of CD, then you can compute for the deformation. So, the unknown here is actually deformation. Ano? So, by substitution, we have 4.6 times 10 raised to negative 4. Ngayon, yung ano ba yung length ng CD, we will just have to utilize the right triangle for that. Titignan natin sa given, meron tayong right triangle dyan. Ito. Because we need to determine the length at CD. So, 52 degrees yan. Ito, 2 meters. Okay? So, this is a right triangle by function of what? By cosine function. Opposite, adjacent is 2 meters all over the length of CD. So, therefore, the length of CD is 2 all over cosine 52 degrees. Yan. Length of CD is 2 all over cosine 52 degrees. We will be having a length of 3.25 meters or 3,250 millimeters. Okay? So, right there and then we can get the delta or equivalent to 1.495 millimeter. Okay, so this is for problem number 5. Okay. So, we'll now proceed to examples of axial deformation. So, kapag axial deformation lang class, if we have a uniform cross-section, sabi natin, 3 conditions for the strain or for the stress to be constant as well as the strain. So, 3 conditions for strain to be constant. So, number 1, dapat uniform cross-section. Number 2, it must be homogeneous, or the material should be homogeneous all throughout the section. And then number 3, the load must be axial. So if we met these three conditions for strain, then we will apply all our formula involving the strain linearly. So when we say linearly, ito lang. Sigma is equal to P over A. Strain is equal to deformational over length. And then E is equal to stress over strain. So knowing these three formulas, we can have the deformation to be equal to PL over. So kapag hindi uniform yung ating cross-section class, we will use the integral calculus, because sometimes, ito nga, as an example, we have here a tapering flat bar. Therefore, at every section, iba-iba na yung ating cross-sectional area. That is why there will be a reference X here, and then we will just consider a certain strip and then integrate from the boundaries of X all over the length. That is why sometimes if we do not have or a tapering material, or if we do not have satisfied these three conditions, especially in the cross-section part, then we will be having a integral calculus portion to solve for the unknowns. So later on, we will discuss this derivation. Ito, yung rod of a unit mass suspended vertically when we have here a bar that is suspended from a ceiling. Ito dati na meron tong W. Meron na yung dating W. It will cause a deformation due to the weight. Ngayon, kapag dinagdagan mo yan, it will have a uniform deformation due to P. Okay? So, P will have delta P, and weight will have delta W. So, saan mag-e-effect yung delta W? Kasi yung W nasa gitna, or is located at the centroid or the center of gravity. So, yung distribution niyan magsisimula lang sa L over 2. Dito siya magde-deform. Okay. So, ang binubuhat niya lang is the upper portion, right? So, the weight or the self-weight being carried by the member itself is the upper fiber only. Yung lower fiber, kasi nga, we have said that the location is located at the centroid. Okay, so the element on the upper portion is being stretched, but the element below this centroid does not have any residual stress. Okay, so that's it. So we have also the stiffness K here. It's just simply equal to the force all over delta. Okay, so perhaps we can end with this one. I hope you first practice these illustrative examples on your material, and then we will go over with the discussion of the solutions. Okay, so thank you and have a good day. So get ready for another lecture tomorrow or the next meeting.